So today we are going to solve few numericals on X-ray, and the first numerical problem is find out the energy in joule and electron volt of an X-ray photon of wavelength 20 angstrom. So there is the X-ray photon of wavelength lambda is equal to 20 angstrom. So this is given, and we have to calculate the energy in joule as well as in electron volt. Now we know the formula E, energy E of a photon of frequency nu is h nu, and we know that nu is the frequency, then nu is c by lambda, so the energy E is equal to hc by lambda. Now we have to put the value of h, that is the Planck constant, c is the speed of light, and lambda is the wavelength of the X-ray photon. Now put all these value in this equation and we will get the energy. So here E is equal to h, that is Planck constant, 6.626 into 10 to the power minus 34 joule second. C is the speed of light, that is 3 into 10 to the power 8 meter per second, divided by lambda. Lambda is 20 angstrom. So 20 angstrom. Now we know that 1 angstrom is 10 to the power minus 10 meter. So 20 angstrom is 20 into 10 to the power minus 10 meter. So this is, we put all these values in SI. So the energy will be in joule. Now if we calculate this, that is 6.626 into 3 divided by 20 into 10 to the power, so this is minus 10, so minus 10 plus 8, so 18, so this is equal to minus 16, 34 minus 18, so this is 10 to the power minus 16 joule. Now if we calculate this, then we will get 0.9939, 0.9939 into 10 to the power minus 16 joule. So the energy value is 0.9939 into 10 to the power minus 16 joule. So we have to also find the energy in electron volt. Now we know that 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. Here it is 0.9939 into 10 to the power minus 16 joule. So we have to divide this value by 1.6 into 10 to the power minus 19, because 1 joule is equal to 1 divided by 1.6 into 10 to the power minus 19 electron volt. So 0.9939 into 10 to the power minus 16 divided by 1.6 into 10 to the power minus 19. This is approximately equal to 621 electron volt. So the energy of the X-ray photon in electron volt is 621 electron volt, and in joule is 0.9939 into 10 to the power minus 16 joule. Now next problem. Here it says an X-ray tube operates at a voltage of 50 kilovolt. Calculate the minimum wavelength of the X-rays produced. So the X-ray operates at 50 kilovolt. So the energy of the X-ray photon is 50 kilo electron volt. 50 kilo electron volt, that is 50 into 10 to the power 3 electron volt, and we know that 1 electron volt is 1.6 into 10 to the power minus 19 joule. So this is equal to 50 into 10 cube into 1.6 into 10 to the power minus 19 joule. We have to find the minimum wavelength of the X-rays produced. So the minimum wavelength, let's say this is lambda, so the minimum wavelength is lambda. Then we know that E is equal to hc by lambda, or lambda is equal to hc divided by E. So put the values of hc and E. So here H is equal to 6.626 into 10 to the power minus 34. C is the speed of light, that is 3 into 10 to the power 8 meter per second. And E is the energy of the X-ray. So this is equal to 50 into 1.6 into 10 to the power 3 into 10 to the power minus 19, that is 10 to the power minus 16, that is minus 19 plus 3. So joule. So the wavelength lambda is in meter. Now if we calculate this value, then we will get 2.48 into 10 to the power minus 34 plus 8 into 10 to the power plus 16. So this is equal to 10 to the power minus 11. This is equal to 10 to the power minus 11 meter. Now if we convert this unit, that is meter, to angstrom, we know that 1 angstrom is equal to 10 to the power minus 10 meter. So this is equal to 0.248 into 10 to the power minus 10 meter. We can write this easily, because 10 to the power minus 11, we can break this into 10 to the power minus 10 into 10 to the power minus 1, that is by 10. So this is equal to, now 10 to the power minus 10 meter is equal to 1 angstrom. So this is equal to 0.248 angstrom. So the wavelength, minimum wavelength of the X-rays produced is 0.248 angstrom. Now the next question is, an X-ray tube can operate at different voltages. If the tube operates at 60 kV, the minimum wavelength of the X-rays produced is found to be 0.0207 nanometer. Calculate the minimum wavelength if the tube operates at 80 kV. So when the tube, X-ray tube operates at different voltages. When the tube operates at 60 kV, so the energy of the X-ray photon will be 60 kV, 60 kilo electron volt, keV. Let's say this is E1, and the wavelength of the X-ray produced, minimum wavelength is lambda 1 is equal to 0.0207 nanometer. 1 nanometer is equal to 10 to the power minus 9 meter. Now we have to find the minimum wavelength if the tube operates at 80 kV. So when the tube operates at 80 kV, the energy, the maximum energy of the X-ray photon will be 80 kilo electron volt. So 80 kilo electron volt. And let's say the minimum wavelength is lambda 2. So we have to find this value, lambda 2. Now we know that energy E is equal to hc by lambda. So E1 is equal to hc divided by lambda 1, and E2 is equal to hc by lambda 2. So let's say this is equation 1 and this is equation 2. Now divide 1 by 2, that is E1 by E2. So E1 equal to hc by lambda 1 divided by E2, that is hc divided by lambda 2. Now hc cancels out. So E1 by E2 is equal to lambda 2 by lambda 1. From here we can write lambda 2 is equal to lambda 1 times E1 by E2. Now put all the value of this, that is lambda 1, that is 0.0207 nanometer, and E1 is 60 kilo electron volt by 80 kilo electron volt. So we are dividing both the energies, so the unit cancels and the unit of the lambda 2 is nanometer, as we have put the value of lambda 1 in nanometer. So now if we calculate this, that is this 0 cancels, and if we multiply 0.0207 into by 6 into 6 by 8, we will get 0.0155 nanometer. So the wavelength, minimum wavelength of the X-ray photon if the tube operates at 80 kilo volt is 0.0155 nanometer.